Okay, in this lesson we're going to be talking about the P minus MQ method and Descartes Rule of Signs. Two more methods helping us finding the roots of polynomial functions. And these two methods can be used in addition to what we talked about in the last lesson, the rational roots theorem and the upper and lower bounds. Not really in place of, but in addition to help us to find roots or to narrow down our list of roots from the P over Q and upper and lower bounds. So let's start with the P minus MQ method. So this is what we're doing. Oh, and we're struggling. Yeah. Alright, so P minus MQ method says if P over Q is a root of a polynomial, then P minus MQ must divide evenly into F over M. Okay, so what does that say? That says that if we have one of our possible factors, P over Q, for it to be a root, then the P minus some number M times Q must be a factor of F of that number M. Alright, let's look at an example. So we've got F of X, this function. We've got a fourth power function. So we should expect 4 roots. They could be rational, they could be irrational, they could be imaginary, but it should have 4 roots. So if we do our P over Q method, the rational roots theorem, then here's our possible rational roots. So any combination of 15 over 2 and any of their factors. We got our plus and minuses here. When we do the P minus MQ method, we want to split those possible rational roots up into our positives and our negatives. We also want to leave them as fractions. Okay, so even if something can be simplified, like 15 over 1 can be just 15, we want to leave it as 15 over 1. Okay, so we've got our positive and our negative split into 2 groups. They're all fractions. So let's start off by letting M equal -1. So we're only going to use 1 and -1 for our M value, just to make things simpler. And you can plug in any number you want to, but to make this whole to make it act an actual shortcut, then we're going to just use -1 and 1. So if we try -1, then if we do F of -1, we can do synthetic division and find our remainder. Our remainder is -48. So -1 is not a root because we didn't get a remainder of 0. It's also not a lower bound. Now remember, a lower bound alternates non-positive, non-negatives. We have positive, negative, positive. This guy would need to be a negative or a 0, and it's not. So it's not a lower bound, not a root, but we've got this -48. So that's our remainder, which means that F of -1 is -48. So if we use our P minus MQ method, that means that P minus -1 times Q, which you can maybe see now why we use -1, because P minus a -1 Q is the same thing as P plus Q. So it's got to go evenly into F of -1, which is -48 here. So remember, P is the numerator of the possible rational root, Q is the denominator. So we can go through our list of roots and pick out, we can just go left to right and see which ones P plus Q, or in this case numerator plus denominator, is a factor of -48. If it's not, then we can cross it out. We don't need to do synthetic division with it. Adding the top and the bottom will be a lot quicker than doing synthetic division with all of those roots. Okay, so one of our possible roots was -15 over 1. Well, if we take -15, add 1, that's -14. -14 does not go into negative 48. So negative 15 over 1 is not a root. We can cross it out from our list. Okay, let's look at positive 15 over 1. 15 plus 1 is 16. 16 goes into 48 3 times, or in this case negative 48 negative 3 times. So this doesn't make it a root, but it's still in the running. It made the first cut. So it's still a possibility. So we want to either circle it or just leave it alone. Don't cross it out. So we can go through each of our possible roots and just add the top and the bottom, see if they're a factor of, in this case, 48, and then we've kind of narrowed down our list to a much easier to manage list. Okay, if it didn't narrow it down enough, then we can pick a different m value. Okay, so we can say, well, let's pick m equals positive 1. Okay, again, to make it a little bit easier on us. So here's our list after m equals negative 1. Okay, we're kind of skipping some steps for the sake of time in this video. So that's still 10 possible roots. So that would be 10 times that you'd have to do synthetic division, and that takes a little bit of time. So if you want to try m equals 1, maybe to narrow down some more of those, that might benefit you in the long run. So p minus mq, if m is 1, that's going to be the same as p minus q. So let's go down. Let's see what f of 1 is. So synthetic division, where our c is 1. Where are you going? Where are you going? Come back. Alright, so our c is 1. Let's see, should be a line right here. Synthetic division is already done for us for the sake of the video. Then we get 8 as our remainder. So the remainder is 8, f of 1 is 8, according to the remainder theorem. So p minus q must divide into, or must be a factor of 8. Okay, so factors of 8, if you want to keep those in mind, we've got 8 or negative 8, 4, negative 4, 2, negative 2, and of course 1. Alright, so go through that list of possibilities that you narrowed down from negative 1. That was up here. So if you go through each one of those, so for instance 15 minus 1 is 14, that's not going to work. 5 minus 1, that works, so you would keep that. 3 minus 1 is 2, so that works, so I would keep that. And again, these don't mean that these are roots, they just made the next cut. 1 minus 1 is 0. 1 minus 2 is negative 1, so that works. Now we get into our negatives. You got to be careful with our negatives. Negative 5 minus 1 is negative 6. That's not a factor of 8. Negative 3 minus 1 is negative 4, so we can keep that one. Negative 5 minus 2 is negative 7. Negative 3 minus 2 is negative 5. Negative 1 minus 2 is negative 3. Okay, so by doing this p minus mq method again, look at how many we crossed out with only doing synthetic division once. We crossed out 1, 2, 3, 4, 5, 6. So now we've narrowed it down to only 4 possible roots. So we've got 5, 3, 1/2, and negative 3. So now I feel pretty comfortable doing synthetic division 4 times as opposed to 10 times. So you could go through, do your synthetic division. Let's do that. So 5 is one root, so let's say we're going to do synthetic division on 5. Our original function, let's see, was 2, negative 7, negative 7, 35, and negative 15. Okay, so for synthetic division, draw a horizontal line, bring down the first 2, times 5 is 10, We get 3 times 5 is 15. We get 8 times 5 is 40. Ooh, that's going to be a big number. 75 times 5 is, I don't know what it is, but we're definitely not going to get a 0. Okay, so we don't need to go on. So 5 is not a root. Okay, let's try another one. Let's try 3. Okay, so 3, again, we've got 2, -7, -7, 35, and -15. Okay, bring down your 2. 3 times 2 is 6. 3 times -1 is -3. 3 times -10 is -30. 3 times 5 is 15. And look here, we've got 0 is our remainder, so that makes 3 one of our roots. It's always a good feeling when you find one. Okay, let's try 1/2. Okay, so now remember we can use this this polynomial here with the 3x minus 3 factored out to save us a step or two. And it'll also allow us to, when we get down to a quadratic or a linear, that we can just solve it in equation form instead of doing synthetic division. Okay, if we have any irrational roots, we're going to need to do that. So bring down your 2. Half of 2 is 1. Half of 0 is 0. Half of -10 is -5. And we've got another root in 1/2. Alright. So now let's try -3. Okay, and again, we can use our next simplified row. We've got 2, 0, -10. Okay, bring down the 2. -3 times 2 is -6. -6 times -3 is 18, and that's going to be 8, so that's not going to work. Okay, so we've got 2 positive rational roots in 3 and 1/2. So, since this was a polynomial to the degree of 4, now there should be 2 more roots. So let's take our simplest form of our function. Let's set up an equation. So we know that if this is our constant, this is our linear term, this is our quadratic term. So we're going to have 2x squared minus 10 equals 0. So if we solve that, add 10 to both sides, divide by 2, and square root both sides. X is, don't forget, plus or minus root 5. Okay, so there's our 2 irrational roots. So finally, our linear factorization, okay, or our factored form, we've got our function f of x. Okay, and our factors, we have 1/2. We have, let's see, what was our other factor? 3. So x minus 3. Oh, come on back down. And then we've got our 2 irrational factors, x minus root 5 and x plus root 5. Okay, so our linear factorization is done. And if you'd like to multiply this first guy by 2, so we don't have a fraction in there, then you would get 2x minus 1 in place of this guy. Okay. So, in summary, P minus M cubed. I want to pause this and jot this down. This is a good step-by-step how to do P minus M cubed method. So, first thing you need to do is do the P over Q method for finding all the possible rational roots. Okay, make sure to leave each root as a fraction, separate it into positive and negative. Start off with -1 as your M, just for simplicity's sake. Find out what f of -1 is, and then cross out any P minus P over Q's where P plus Q is not a factor of that number. Okay, so then you got your reduced list. You can either go ahead and do synthetic division if you crossed out a bunch, or let M equals 1, do another iteration of the P minus MQ, and then see what you've got after that, and then do synthetic division to find the roots. Okay, so let's look at Descartes' Rule of Signs real quick. Descartes' Rule of Signs is another helpful tool when finding the roots of a polynomial function. Okay, Descartes' Rule of Signs tells you how many positive or negative real zeros the polynomial has. Okay, so this talks about not just rational, but our real zeros, so rational and irrational, but not imaginary. Okay, it can save you a lot of time because it'll let you know kind of what type of numbers you're looking for, positive or negative, and indirectly imaginary numbers. So to do Descartes' Rule of Signs, we're going to be looking at the variation in sign of our given function. Okay, so it's got to be in standard form, our given function. So let's look at P of x. We're given P of x here as x to the fifth minus 2x cubed plus 2x squared minus 3x plus 12. So we're looking for variations in sign, so literally the pluses and the minuses. So we start off with a positive. So x to the fifth is a positive, and then this next term is a negative because we're subtracting. Then we have a positive, and then we're subtracting as a negative, then we're adding a positive. So we've got from positive to negative is one change in sign, negative to positive is a second change in sign, positive to negative is a third change in sign, and then lastly we've got negative to positive is one more change in sign. So we have 4 changes in our sign. Okay, if we have any zeros, any missing, like for example our x to the fourth term is the coefficient is 0, we just ignore that, we leave it out. If it's in standard form, we can do it from there. So Rule of Signs says number of positive zeros or positive roots of our function P of x is either equal to the number of variations in the sign of P of x, and our example was 4, or any multiple of 2 less than that number. So in this case we could have 4 positives or subtract 2, we could have 2 positives or subtract 2 until we get to 0, we could have no positive roots. So that tells us the number of positive roots. To find the number of negative roots, then we want to find P of negative x. So we're going to go in and substitute a negative x in our function everywhere we see an x, and then do the same thing. Look for variations in sign. Alright, so P of negative x. If we replace negative x into our function and then of course simplify it, so any odd degrees will be negative, any even degrees will stay positive, or the sign won't change, I should say. Okay, so let's look at our P of negative x simplified. We've got a negative to a positive, so that's 1. Give a little tally mark maybe. Positive to a positive doesn't change, positive to a positive doesn't change, positive to a positive doesn't change again. So we've got to have just one negative root. So for our negatives, we have just one root. Okay, now since p of x is a 5th degree polynomial, looking at the exponent of our leading term, then it's got to have 5 zeros. It's got to have 5 roots. So it might help to have a table to organize all these different possibilities. Because again, we said it could have 4, 2, or 0 positives. And directly, Descartes' rule of sign doesn't tell us anything about imaginaries, but since we know the total number of roots has to be 5 in this case, then we can set up a nice little table where we've got our positives on one column, the negatives in the next, and then if we list our possible positives to start off with. So we have 4, 2, or 0 possible positives, and our negatives could only be one negative because 1 minus 2 would be a negative number. We can't have a negative number of negatives. That would explode brains. So imaginary roots are going to be whatever's left over to make sure that we have 5 total roots. So 4 and 1 is already 5. So if there's 4 positive roots, then there can't be any imaginaries. But if there's only 2 positive roots, 2 and 1 makes 3. So we need 2 more roots to get to 5, because remember, these always have to add up to be 5. So then we would have 2 imaginary roots. And likewise, 0 and 1 is 1, so we would need 4 imaginary roots for that possibility. Okay, so again, Descartes' rule of signs doesn't tell you any specific roots, doesn't necessarily narrow down our list, except for the fact that it tells you the possibilities of the number of positive, negative, and then imaginary roots. And again, these are real roots. These don't necessarily tell you the rational roots. So it could also be the irrational roots with a square root symbol. Okay, so this example here, we're going to work through as fast as possible. Alright, just want to check and see how that was looking. So, given f of x, we've got a polynomial to the 5th degree. We want to determine the following: the total number of complex roots. Okay, it's the same as the degree. They tell us right there. So, our degree is 5. So, complex roots is 5. Okay, the possible number of positive roots using Descartes' rule of sign. Okay, so now we've already got it in standard form. So let's count our sign changes. So from positive to negative, that's 1. Negative to negative is not. Negative to positive is another. Positive to negative is another. And negative to positive is another. So that's 4 possible roots. And again, we need to subtract 2 until we get to 0. So we could have 4 or 2 or 0. Okay, so negative roots, we need to find f of negative x. So if we plug in negative x for each of our terms, and actually let's do this the shortcut way. Okay, any odd powers, it's going to change the sign. Any even powers is going to not change the sign. It's a nice little shortcut. Okay, odd power, so that negative is going to become positive. Because remember, a negative times a negative is a positive. So any even power, we're just going to get just as if we put in a positive x. Okay, so negative 6x becomes plus 6x, and then of course that doesn't change our plus 8. Okay, so now let's look at our sign changes for f of negative x to find our negative roots. First one is nothing. We've got one sign change here, and then positives throughout the rest. So only one sign change. So one possible negative root. Okay, so our imaginary roots. Well, I need a table to find this, to look up my things, and it's actually going to look just like our previous table. So we've got 4, 2, and 0 for our positives. Didn't leave myself a whole lot of room for that. It's alright. For our negatives, our only possibility is 1. So then if our total has got to be 5, since our degree is 5, our imaginaries, 4 and 1 is 5, so no imaginaries for that possibility. 2 and 1 is 3, so we would need 2 and 4 for our last possibility. So now our imaginaries will always come in pairs. Always got the positive and its conjugate to go with imaginary. So these will always be even numbers or 0. Okay, part E. Using upper and lower bounds and the P minus MQ method, determine all roots of f of x. Okay, we're going to skip the bounds part, and we're going to go straight to the P minus MQ method. So, let's start off. Let's let m equal -1. And so, if m equals -1, then we're looking for p plus q, and we need to find our remainder of our function for f of -1. So I'm going to do synthetic division. Alright, so my coefficients, let's see, are 1, -3, -5, +5, -6, and +8. Okay, synthetic division, bring down the 1. So we're going to change the sign each time. So we get 20 as our f of m, f of -1. So this is the number we're looking for factors of when we do p plus q. So in order to do p plus q, we've got to have our p's and q's. So from here, I'm going to let you guys finish this one up in your notes. So again, the next step, you want to find all of your p over q's. Then you want to see which ones p plus q will give you a factor of 20. Keep those, cross out all the other ones. And once you've done that, if you need to do another round, let m equal 1. And for your final answer, write f of x as a complete linear factorization, totally factored out. Okay, so we talked about P minus MQ method and Descartes Rule of Signs, 2 ways of hopefully helping you to find the roots of a polynomial function by hand. A little simpler, maybe saving some time, saving a lot of synthetic division work.